So I'm going to talk about privacy on Swarm. Swarm is the subsystem for Ethereum where distributed applications can store large amounts of data which would be prohibitively expensive to store on the actual blockchain. And there's an obvious requirement for some of that data to be private that is only accessible for parties that are authorized to see it. Now, let me just give a brief outline of my talk. So first, I'm going to give you the minimum necessary information about how data is represented in Swarm. Then I'm going to discuss how content is actually symmetrically encrypted. Encryption is crucial here because in a distributed system, unlike in a centralized counterpart, it is impossible to control the access of people to data or other entities to data by providing or not providing that data, because all the data is by definition public. So the only way to restrict access to data is to encrypt it. And in the third part of my talk, I'm going to discuss how key management is done and how access control is actually implemented. So first, a brief introduction. Swarm consists of these 4 layers. So at the bottom is a layer where we have chunks of data, each of them at most 4 kilobytes in size. So they're fairly small, fixed-size chunks of data. And the network only knows about this layer. So when Swarm nodes communicate with each other, all the communication happens in reference to these little chunks. Above that layer, we have a layer which represents big binary blobs, or potentially big binary blobs, which have an arbitrary length, well, whatever is expressible in 64 bits, and there's no metadata attached to it. So on this layer, every blob is identified by the hash of its root chunk, because these blobs are actually organized into a tree of chunks, which I'm going to show you a little bit later. And above this layer, we have a virtual content-addressed web server, which has all the typical metadata of web content, like content type, HTTP response status, and things like that. And above this layer on top, we have the Swarm-hosted distributed applications, which can, if they want to, access the 2 layers below them. But a typical application would only access the virtual web server. So what's inside the chunk? A chunk consists of 2 parts. First is what we call the span, which is kind of the file length of the file represented by this particular chunk and the subtree of other chunks that are below it, and at most 4 kilobytes of payload data. So if the span is less than 4 kilobytes or equal to 4 kilobytes, then it is basically, the payload is the data. So the payload is the binary blob. If the span is more than 4 kilobytes, then this chunk is an intermediary chunk, which means that it's a non-leaf node in a tree, and it has references to subtrees, not the actual content. So here's the representation. So here's how you would store like 10 kilobytes of data in Swarm. So you have the root chunk, which declares a span of 10 kilobytes. And since 10 kilobytes require at least 3 chunks, it has 3 references to 3 chunks. And those 3 chunks have 4, 4, and 2 kilobytes of the data. So this is how 10 kilobytes of data would be represented inside Swarm, and it takes 4 chunks to represent it. The layer above it contains objects which are called manifests, which are Merkleized key-value databases somewhat similar to Ethereum state trees. And the key in these databases is the path that you would use in the URL, and the value is a reference to the content and all kinds of HTTP metadata that you can think of. Typically, and as a minimum, you need to have content type. So if you address a collection of files in Swarm, then what you actually enter is either the hash of the root chunk of the manifest or an ENS name which contains this root hash. So that is how a Swarm site is structured if it's unencrypted. And are there any questions actually at this point? No? OK. So then I will go on to explain how can we, so all this was completely unencrypted and is completely unsuitable for uploading your home directory, for example. So in order to overcome this problem, we're going to introduce symmetric encryption to Swarm. Symmetric encryption means that you use the same key to encrypt and to decrypt. The actual encrypting schema is counter mode encryption. This is a diagram from the Wikipedia page for modes of operations of block ciphers. So this is currently the most widely used and most secure mode of operation of a block cipher, because it is very easy to reason about. And what it actually does is that you can see that the actual one-way function, the block cipher, is always used in encryption mode. So you don't use the reverse direction of the block cipher. And what it achieves is that it takes a key and, using a counter, creates a pseudo-random bit stream out of it, a so-called key stream. And then this key stream is XORed with the plaintext in order to get the ciphertext, or it is XORed with the ciphertext in order to get back the plaintext. And because of the counter mode, it is actually possible to do partial decryption, where you don't have to generate the whole key stream, only its section which covers the data that you're interested in. So this is the basis of what we use. But also please note that here we don't use many of the properties of the block cipher. The only property that we use is the one-way function nature, the random oracle nature of the block cipher, namely that given the output, it is hopelessly difficult to find a matching input consisting of both the key and the actual input of the block cipher, which in this case is the nonce and the counter. So for our purposes, we have created a special case of this structure. Oh, sorry, wrong button. So instead of the block cipher, we use the SHA-3 hash function, and we use it twice. So what's the justification for this? First of all, SHA-3 is already used in Ethereum for identifying all kinds of things. So the block hash is in SHA-3. The links inside the state trie is SHA-3. And also in Swarm, the references that we use are also SHA-3. So basically, as long as SHA-3 is secure, those parts are secure. And if SHA-3 is broken, then it's broken anyway. So in order to keep the attack surface small, in order not to introduce other cryptographic primitives, which would constitute yet another point of attack, we stick to SHA-3, because if SHA-3 is broken, we're screwed anyway. And we can use SHA-3 for the purposes of counter mode encryption. But why do we use it twice? That's a more interesting question. So using a hash function twice is still a hash function. It still has the one-way property. However, it gives us one extra opportunity that in linking encrypted data to the blockchain, and in particular to smart contracts, because it becomes possible to reveal that intermediate step, so the one that is between the two SHA-3 function calls. And if you reveal the pre-image of the second encryption, it will not reveal the key, it will not reveal the counter, but it lets you decrypt the data, which means that you can selectively decrypt a small part of the chunk, provide a Merkle proof that it is that part that you're uncovering, submit it to a smart contract, and since the Ethereum virtual machine also has SHA-3 as a precompile, you can actually verify that piece of content. Now, those of you familiar with cryptography would immediately notice that this schema, this proposed construction, is vulnerable to what cryptographers call an existential forgery. Because if I reveal the wrong pre-image, not the actual one, I hash it, and then I XOR the result with the ciphertext, I will get some plaintext. And I can still claim that this was the original plaintext, and with this particular pre-image, I can produce this ciphertext, which is the encrypted content that's stored in Swarm. But existential forgery turns out to be not that much of a problem. Because with existential forgery, you can find some matching plaintext, but you cannot place any constraints on them. So if there's any integrity protection built into the data itself, then you will not be able to forge it at all, because existential forgery will not allow you to actually fulfill the constraint of the integrity protection. And as it turns out, there's plenty of integrity protection there. So in the intermediary chunks of the Swarm representation of binary blobs, the integrity protection is the very fact that, hey, the plaintext happens to be the hash of another chunk. And with existential forgery, if you can do that, it implies that you can actually find a collision in the hash function, which by definition you can't. Or by assumption, to be more precise. By the assumption of security of SHA-3, you can't. So the intermediary chunks are already secure against existential forgery. And for the actual content, you do have to provide some integrity protection. So whenever you need to reveal part of the actual content, there also needs to be some hash or some MAC or some digital signature that integrity protects the content that you reveal. And in that case, you won't have a problem with existential forgery. And therefore, you can make statements in smart contracts about the plaintexts of files that are only available in encrypted form in Swarm. And obviously, you reveal parts of it only in case of a dispute. So that's the rationale behind using SHA-3 twice. So just to recap, the references in encrypted Swarm consist of the hash of the ciphertext and the corresponding decryption key. So instead of the 32 bytes of the hash in the unencrypted Swarm, here we have twice as long references, but otherwise everything else stays the same. And in particular, the API itself is completely unchanged. So if you have some distributed application that you have put together on Swarm, for example, if you try to use the applications that are provided with Swarm as example application, like the photo album or the Swarm Explorer or the text editor, So if you use any of those distributed applications, if you turn on encryption, they will just work without any change to the code because the API is unchanged, and these applications do not assume the length of the reference. The only cryptographic assumption that we make is the security of SHA-3, which means that our attack surface is very narrow, and so much hinges on SHA-3 in Ethereum anyway that if SHA-3 is broken, then we have bigger fish to fry than the problems of swarm encryption. But as long as SHA-3 stands up, which we hope is going to be a very long time, then the proposed scheme is provably secure. And the most important property is that this is all very smart contract friendly, meaning that smart contracts can depend on content inside encrypted swarm content. So that's the symmetric encryption part. Any questions at this point? No? Okay, so the last part of my presentation is about the key management, like how do we make sure that these symmetric keys that encrypt the swarm content get to become available to exactly the entities to which we want to reveal the information and not anybody else. So basically, this is access management. So the cryptographic primitive that we use here is the elliptic curve version of Elgamal encryption, which means that the identity is the SecP 256K1 public keys. It's the same public keys that are used for Ethereum addresses. You can keep those, the corresponding private keys in hardware wallets. Adding swarm decryption functionality to any of them is a trivial matter because it uses the exact same cryptographic primitives as Bitcoin or Ethereum and the vast majority of other blockchains. The plain text is the symmetric key. So the only thing that you encrypt using Elgamal is the symmetric key that we used in the previous section. And the way we encrypt it, it's there. So we generate some random k. We multiply a generator point by that k. And the ciphertext is going to be a pair, which has this capital K point, which is the generator point multiplied by the random index. And then the public key of the party that can decrypt it multiplied by this k, the small k, and combined in some reversible operation, for example, XOR, with the actual ciphertext. And the decryption, you can see there how it works. So here we're using, again, the same cryptographic primitives on which the security of the whole Ethereum hinges. We don't introduce anything new or controversial. And we, crucially, do not increase the attack surface by introducing new cryptography. So this is the exact same elliptic curve cryptography that Ethereum uses for digital signatures. And how do we manage those keys? How do we enumerate the people who have, or the entities that have read access to a particular file? We have ACLs, access control lists. The reference to the ACL concerning a particular file or subdirectory inside Swarm is simply added to the manifest as metadata. And what's inside this manifest is, and another piece of metadata added is the public key of the owner of the ACL. So the entity that has the power to modify the ACL, who has the permission to give and take permissions. And the ACL itself is, just like the manifest, a key value database. It's actually in the manifest format. It's exactly in the same format as the manifests in Swarm. And the key is a Diffie-Hellman shared secret of the owner of the manifest together with the public key of the permitted party. Why do we do this? We do this so that a party that can decrypt, that has access to a manifest, can very quickly retrieve the encrypted secret key. Moreover, a party that doesn't know whether or not they have access can very quickly check. So they calculate, they look at the manifest, they take the public key of the ACL owner, they calculate the Diffie-Hellman shared secret, and then they use that as a lookup key. So they can very quickly check whether or not they have been granted permission to read. Yet, they cannot see, neither them nor anybody else can see who else has read permissions. The only thing that is apparent from a ACL is a lower bound, sorry, an upper bound of how many members the ACL list has, because that's the length of the ACL, but the owner is perfectly justified to stuff it with a lot of garbage if he wants to keep it a secret how many actual entities have access to an encrypted entity, an encrypted file. And the value is the Algamahl encrypted content key that I have shown in the previous slide. So you have this ACL. What you do is you look up whether or not you have permission to read this. If you do, then you decrypt the corresponding Algamahl encryption with your private key, and that gives you the symmetric key with which you can decrypt the swarm content. And so again, to summarize what it means to the end user, we're using hybrid encryption. So that means the asymmetric encryption of a symmetric key, and for everything else we use symmetric encryption, which means that large files and collections of files only need to be encrypted once. You don't have to re-encrypt them if you want to give read permission to yet another party. Modifying ACL requires a very small number of new chunks to be generated because it's basically modifying a Merkle structure. And if you want to store the root in ENS to have it a name, then a single transaction on the Ethereum blockchain. So each time you make modifications to the ACL, no matter how complicated those modifications are, you can completely change the scope of the audience to which your content is available. And yet, the only thing you need to do is update a single root hash inside ENS, a single transaction to the Ethereum blockchain. So it's very cheap. So read access in this distributed model equals ownership of the key and the ability, therefore, to decrypt encrypted content. And write access is simply your permission to modify the corresponding record in the ENS resolver. So it is governed by the smart contract that is registered as the resolver for that particular ENS name. So that's how it works. So thank you very much, and I'm open for the Q&A session.
No, I don't think that. Oh, okay. When you want to, like, let's say, have random write access into the file, do you have to re-encrypt the entire, like you have blocks all over the network, and you need to decrypt, write your data, but it might be more than 4 kilobytes, so you need to cut it and paste it in the following blocks, and everything gets shifted. What is the performance of that? I'm just wondering.
So let me go back to how counter mode encryption works. Here. So if you just change data and don't move data, like don't insert and don't remove, then you only need to modify the corresponding chunks, and also walk all the way up the Merkle tree to the root, which is a logarithmic number of chunks that you need to modify, which is a small number. And you also need to calculate a logarithmic number of hashes and update one root hash in the end in ENS. So any modifications that doesn't involve actually changing the distance between information within the file, so which is just overwriting, is very cheap. It's actually so cheap that we already have a fuse integration within Swarm, so you can actually mount a Swarm collection and have POSIX level file access to an encrypted or non-encrypted Swarm volume and change stuff within it. So that thing is cheap. If you need to insert stuff or remove stuff, that's expensive, but that's expensive not because of the encryption, that's expensive because how this whole thing is organized, and that is assumed to be expensive in POSIX as well. So whenever you have any data manipulation model that can live on top of a POSIX file system, you can also have it on top of Swarm, because what is assumed to be cheap in POSIX file model, it's also cheap in Swarm, if that answers your question. Yep, do we have a question there?
It's worth mentioning that it's equally cheap to modify the access control.
So is there a part in this scheme where you overcame the malleability of El-Gamal encryption? For it's greatly not advised to use El-Gamal in public crypto systems because of this malleability. If I capture you a message encrypting something, I can create another ciphertext of my message under your key, and this could lead to decrypt your storage on a public network. So El-Gamal by define is homomorphic and malleable. Thus, it's not used in systems where I can see your encrypted messages.
Okay, so this is a somewhat involved topic, so let's go back
Okay.
here. It's a good question, though. I like it. So El-Gamal type encryptions indeed do suffer from this, that even if you don't know the ciphertext, you don't know the plain text, don't know the plain text and don't have the private key to decrypt it, you can still change it in such a way that the content will be encrypted to some other key, right? So that's the concern that you have. Now, you can change it means that you can insert somewhere what you have changed. But as you can see, the ACL list itself is integrity protected. So this is not a communication protocol. This is a storage protocol, which means that you can eavesdrop on it, but you cannot insert messages because the whole thing is integrity protected through a chain of hashes that is rooted in the blockchain. So the fact that you can apply a transformation to the encrypted content does not mean that you can actually fool other parties by inserting this encrypted message into any data stream, because we don't have a data stream. You're welcome. Yep.
In principle, it would be easy to check the owner of the access control list as the same as the owner of the ENS, because the owner of the ENS can also be like a private key Ethereum address. Is there any reason why you want to have an extra layer in between to have a manifest, or can that be the same? Or would you, in other words, would you recommend that if you encrypt a site, then you use a different public key than what you have for ENS?
Well, there's one. So I would like to leave this this degree of freedom open. So I do not want to hard link the public key of the access control list to the public key of the owner of the ENS entry. So I would like to allow for these two things to be different, because the key, the shared secret that you compute between between two known public keys, even though you cannot reproduce it, you can recognize it, which means that if you always use the same public key for access control lists, and you give permission to the same entities in different access control lists, you can, so this information that it's the same entity that has access to these different files is revealed, it is leaked. So actually, I would treat the public-private key pair of an access control list as somewhat of a ephemeral encryption. So if you really care about not revealing any information, then you don't reuse that key for different access control lists. Because if you give permission to the same entities, you would have the same key in both ACLs, and you might want to avoid that. So that's why I don't insist on those two keys being the same, and I actually do recommend them to be different.
That is not simply mitigated by adding an extra hash based on the content hash to the decryption.
No, because well, depends on how you add it, of course. So like you can do a key derivation. So basically, to this scheme, you can add the key derivation, but you can also do it like outside of the structure. So of course, you can derive these keys somehow, and it's a good idea probably to derive these keys, because that way you don't have to actually store that many public keys. But even if you're deriving those keys, it is good practice to actually have different keys there, even if they're derived from the same seed. Okay. There's a question up there.
Hi. I assume you used access control list carefully, or you choose it carefully. I just wanted to know, are there any reasons in choosing this one instead of other based security mechanisms, like say, purpose-based, or, yeah, just wanted to know.
So actor-based access control lists are kind of difficult to implement in a distributed setting, because the only thing that you can do is to either allow decryption or not allow decryption by sharing the key. You cannot withhold information, because the information is there, it's accessible. So you cannot say that, hey, you're not authorized because of this complicated set of criteria, therefore I'm not giving you that information. You can do that on a centralized entity, but you cannot do that on a decentralized network. So the only thing that you can do is to encrypt, and if the only thing you can do is to encrypt, then basically your only reasonable option is to turn your access control lists into lists of public key encrypted secret keys. No further questions? Well, thank you so much.